Assalamu alaikum students. So we are continuing our water balance lectures. In the last lecture we talked about uh, the, the difficulty in concentrating urine. We just introduced those topic, the comparison between uh, overhydration and dehydration and the renal response to these two scenarios. So the one being when water is in abundance, uh, and and the kidney responds to that, and the other is when water is scarce. How should the kidney respond to that? I left that lecture with a question: what do you think the kidney would struggle more with, water abundance or water deprivation? We'll be answering that today. So the learning objectives is renal response to overhydration and renal response to dehydration. As you can see, this is not a very busy place here. It's straightforward. However, here you have all sorts of mechanisms, which obviously will take the bulk of this video. So under dehydration, we'll be studying a mechanism called the countercurrent multiplier, the Urea cycle, and the countercurrent exchanger. Okay. So first, let's speak about dilution of urine. Uh, what basically is happening is water is in abundance, or you are overhydrating yourself. Uh, how would the kidney react? What do you expect the kidney to do? You want the kidney to excrete this extra water out and retain the solute. Okay, this is an important point. Retaining the solute, because if you let the solute go as well, then you will again add to the hypoosmolarity, which has been created by your increased fluid intake. So you would want to hold on to the solute, but at the same time get rid of the water. Okay, how does it do? It's rather straightforward. This is where this is what we intend to do: reabsorb solute and not allow water to follow. This is the simple thing. And if you see the nephron, this is how it is. It's the PCT is where pretty much things are fixed. You can't do much here. So the isoosmotic reabsorption of water and solute that I have been talking about initially, this is something which is constant and cannot be changed. Okay, it's the thick ascending limb of Leucophenidae, where you can dissect out the solute from the water. This is also called the diluting segment, as mentioned before. And this is where you separate out, you reabsorb sodium chloride into the interstitium, uh, but water cannot follow it like it follows in the PCT. Here, the water cannot follow, and hence what you have is the tubular fluid becomes dilute because you've removed the salt, and now what remains behind is the water. You can also see these values of osmolarity of tubular fluid, that 300 is what is the plasma osmolarity. So when fluid flows out of the proximal convoluted tubule into the loop of Henle, the osmolarity of the tubular fluid is 300. So this is something very important which one needs to be very careful about in the next slides when we are talking about concentration of urine. Anyhow, so this 300 is the osmolarity of fluid when it enters the loop of Henle, and all sorts of things then happen. Water goes out, which again we will talk in detail about in the concentration of urine scenario, because this segment is permeable to water, not to solute. Okay, so water goes out, the concentration of the osmolarity of the tubular fluid increases from 300 to around 600 at the bend of the loop of Henle, because of water being given out and not solute. And in the thin ascending limb, you have some sodium chloride going out. Okay, these are minor bits, or minor mechanisms rather, in dilution of urine scenario. They assume a lot of importance in concentration of urine. So coming to the thick ascending limb, again, as I said, you will pump out the salt, but the water cannot follow because of the anatomy of the epithelium of the segment. So you can imagine now that the 600 became 100. Osmolarity became so diluted because you did not allow water to go out. Now this fluid will then move to the collecting ducts, where it will simply further decrease in its solute content, because you will have seepage of sodium chloride here and in the inner medulla as well. However, since there is no ADH present, so these segments are ADH sensitive as mentioned before. Since ADH is at a low because the plasma osmolarity is dilute, and for ADH, as you know, that plasma osmolarity needs to increase for ADH to release. So in this scenario, you don't have that ADH. So water in this urine will just flow out. There is no stimulus for water reabsorption because this is a low ADH scenario. So overall, you witness that in this nephron, it's not really struggling for anything. It doesn't need to do much. It just does what it does naturally, and each segment is basically doing its job. There is no going out of the way to do anything significant. Thick ascending limb is again the main character here, and so is the collecting duct. Okay, nothing spectacular is happening. It's just the run of the mill, and no, it's simple diuresis. You let go of the water. This is a diagram to just give you an overview of what we've discussed. So the person was made to drink 1 liter of water, and look how his or her osmolarity changes. So extra water, obviously, this is not required. What will it do is it will bring down the osmolarity of the plasma, and the urine will oblige by decreasing its osmolarity even further down, i.e. diluting itself to get rid of the water. The urine flow, as you can see, has increased. However, the urine solute excretion is kept at a bare minimum. Okay, so the point here is dilution of urine is not challenging, because you have to let go of the water. You don't need to worry about uh, reabsorbing any water or any solute out of what normally happens in the nephron. So the answer to the question of the previous lecture is that dilution of urine is not the challenging scenario. It's actually concentration of the urine. Now, let me take some time here to introduce you to the challenge of concentration of urine. So remember, this is now a dehydration scenario. The body is in dehydration. Okay, water is less scarce. What has happened is that plasma osmolarity has risen because of less water. Now, this hyperosmolar plasma is a problem, because wherever it's going to go, it will affect cell volumes, as we have discussed the process of osmosis and all that. Now, this needs to be addressed pretty quickly, okay, because it will mess up cell volumes in crucial organs like the brain and elsewhere. So the kidney then needs to do something, and this is the scenario, this is the setting, this is the stage. Now, what is the problem? Just just tell the kidney to reabsorb extra water. Now, this is the problem. You see, I've been saying this all along since we've been discussing osmolarity, that water reabsorption is always passive. Okay, so to reabsorb water, you need to have channels along the tubule, along which water can go down its gradient. So wherever there is a natural gradient present between high water concentration in the lumen and low water concentration in the interstitium surrounding the tubule, water will naturally come out. Okay. The second most favored thing for water movement is it tags along sodium, because sodium is a effective osmol. It gathers around water molecules uh, when it's allowed to, and it does not move alone. It always drags the water with it. So that's another way that water tags along. However, this is obviously we're talking about normal stuff. But when you want extra and put air quotes on the extra, now you want extra water to be reabsorbed. You want that that extra water going, which would have gone uh, wasted in the urine. You want that. You want to reclaim that. You want to minimize uh, the the free water that is in the urine. Because why? Because the plasma has become osmolar. You want to reabsorb extra water so that the hyperosmolarity of plasma is addressed. That is the problem. Why is that a problem? You need to create now a situation, because water is always passively reabsorbed. So where will you get the extra drive, the extra punch to get to claim or reabsorb this extra water? For this, you need to have a maneuver. You need to create a trap so that uh, water, extra water, can be reabsorbed. And this is the story now. Okay, this is the challenge of for the kidney in concentration scenarios, which it's not the case in dilution. Okay, now there are three things here which you need to study carefully. Of course, these are not exhaustive videos, and one cannot go into academic uh, very fine details, because that will then take the video's timeline to a ridiculous amount of time. So it's highly recommended that these videos should be used for uh, journal overviews. Also, of course, I will try to pitch in and pack in as much as information as possible. But once again, it's not a replacement for your own study. So please, these are complex concepts, especially concentration of urine. This also has a big big value in your assessment. This is one of the most frequently asked questions in renal physiology, both in Viva and in SEQ. So it's very, very important that when you listen to this, you augment it with reading these concepts from a standard textbook. Guyton is, of course, more than sufficient. You can always refer to BRS for some overviews. Okay. Now, there are two things mainly. One is you need ADH. And I think by now you understand what ADH is, what it does. This is where ADH comes into play at its, this is where ADH is at its most prolific expression. This is where ADH is really required to deliver anti-diuretic hormone. You need anti-diuresis because the plasma has become hyperosmolar. You need anti-diuresis so that water is now extra water is now reabsorbed. So you need high ADH. Indeed, plus high plasma osmolarity is a stimulus for ADH secretion. Okay. Now this ADH is there. You have set up ADH mediated aquaporins in the collecting duct mainly, and now we are set to reabsorb extra water. So the channels are there. However, where is the drive? You need the drive to reabsorb extra water. Remember all of that discussion which I had just now? That can be done by establishing a, a hyperosmolar medullary interstitium. Now remember, this is not the case generally speaking. Generally, the medullary interstitium is indeed, it has more osmolarity than the outer cortical sections of the nephron. And certainly, as compared to plasma, it is hyperosmolar. But in concentration of urine, in dehydration, it needs to be hyperosmolar. So the osmolarity of this interstitium needs to rise many folds to get that extra squeeze of water out of the tubular fluid. And this is that artificial thing, the bumping up of the osmolarity that I was talking about, that the kidney has to do in while it's concentrating urine. So this is called establishing HOMI, hyperosmolar medullary interstitium. The process, how it does it, is countercurrent multiplication. There is a countercurrent multiplier. There's a whole mechanism which we'll go into in a bit. So basically, this establishes the stage, the trap, the magnet for extra water reabsorption, uh, because obviously uh, this is hyperosmolarity. So you have managed to uh, trap or make available extra solutes in the medullary interstitium, so that water has no choice but to come out of the tubular fluid. And and you have already laid down the roads for it by making aquaporins available, because that's what the ADH does. So the roads are there, the drag is there, the traction is there. Water now has really no chance but to come out. Okay, and this is the mechanism by which it does it. At the end of this whole lecture, we will talk about how to maintain this HOMI, and there are challenges for this hyperosmolarity to be maintained. One is immediate, your attention may come to the point that, look, hey, we have created hyperosmolarity in the medullary interstitium, which, by the way, will attract water to come out. Where will the water come out and come into? In the medullary interstitium. So doesn't that throw you off? Doesn't that wouldn't that dilute the medullary interstitium? Well, in theory it should, but it doesn't. Why doesn't it do it? Why doesn't it dilute the medullary interstitium, the reabsorbed water? Is because there is a countercurrent exchanger mechanism which is present in the same area, which takes away that water and does not let HOMI be diluted. Okay, and you need that water anyway. So you don't need that water in the medullary interstitium. Certainly, you need it in the plasma. So of course, the discerning student would have discerned by now that the exchanger is actually the blood vessels, the peritubular network, the vasa recta, which we have mentioned maybe twice or thrice early in the discussion when we were discussing the anatomy of the nephron. These are the vasa recta, the peritubular network, long loops of capillaries which run alongside the long loop of Henle. That some neurons, only 15 to 20% of nephrons that are present in the kidney. You remember all that discussion, and these are the nephrons which are involved in concentration of urine. Right. So this is just an introduction of this rather tricky topic, and we will now go into some details of HOMI and later finish off with how it's maintained. Okay, so again, some background to the countercurrent multiplier now. Remember, we have already discussed ADH in the last lecture. Okay, you know, or you should know how it is, where it is formed, where is it released from, what are the conditions. One is of course hyperosmolarity, another is changes in blood volume. We've done that, and if this is something that you are not clear about, you need to pause this video and watch the water handling one lecture. Okay, and you will understand we have a whole discussion there of ADH. So I'm not going to go into details. I'll just summarize here that high ADH is required for concentration of urine, because this is how you will create, you will allow aquaporins to get inserted in the collecting duct. They're extra, these are water channels. I talked about in the last lecture, talked about the reversibility of this mechanism. This is not fixed as PCT, water reabsorption at the PCT is fixed. This, however, is variable. It only comes into play when you need it, i.e. in dehydration. So ADH I won't talk about. I'll straight jump into HOMI. Now, HOMI is hyperosmolar medullary interstitium. This medullary interstitium, the area surrounding the loop of Henle and the collecting duct, this needs to be flooded with solute, extra solute, so that, as I mentioned, extra water can be reabsorbed. So the thick ascending limb of loop of Henle is where most of the action comes in. And actively, sodium along with potassium and 2-chloride are pumped from the lumen into the interstitium. Again, this is something that we've discussed when we were discussing sodium transport. We discussed the thick ascending limb of loop of Henle, if you remember. And let me just jog your memory. Furosemide was an antidiuretic, I beg your pardon, a diuretic, which blocked that symporter. That's sodium, one potassium, 2-chloride symporter, if you remember that now. So that is the transporter which enhances the uptake of solute from inside the lumen and pumps it into the interstitium. This is the mainstay, one of the mainstays of creation of hyperosmolarity of the interstitium. The number two is urea. Now, this may come to you as a surprise that, of course, your concept about urea is that it's a waste product and it's given out, it's excreted from the urine, and that is indeed the case. However, today you learn that urea is very ingeniously used to add to this medullary interstitium. In fact, it's 50% of the HOMI. So sodium is 50%, and the other 50% is urea. And you will be interested to know that during normal situation, urea does not get concentrated in the medullary interstitium. It's only when ADH is present, as it is the case with dehydration, is when urea can cross from the exiting urine in the medullary interstitium, in the collecting medullary collecting duct, and enter into the interstitium and add to the HOMI. More on this in the urea cycle later on in this discussion. For now, what is enough is sodium and urea approximately account for the 50% each of HOMI that you need to create. Okay. Now, this scary looking diagram is not very scary if you understand the basics of it. So before I go into it, please remember a couple of things. And those couple of things is the way this diagram is made. Firstly, I'll go slow here. These figures, these numbers are osmolarity of the tubular fluid. So if it's inside the tube, it's tubular fluid osmolarity. If it's outside, it is the interstitium. It is the interstitium, osmolarity of the interstitium. As you go along, dip into the inner segment of the interstitium. This is where the medulla is. Okay, and as you go away from the medulla, this is where the cortex is. Okay, so obviously the nephron is arranged in such a way that the long tubule from PCT, which lies in the cortex, then dips to the into deeper into the medulla, the outer medulla, and then in the inner, deeper medulla. These are the long loop of Henle nephrons that are involved in concentration of urine. Okay, so they really loop into the inner medulla and form those hairpin structures. Right. So I have mentioned this, that these values represent osmolarity inside the the tubule, or in the surrounding interstitium. The HOMI that you need to create is in the interstitium here. Okay. The loop of Henle not shown here, but this loop of Henle will obviously go up, make the DCT, and then here it will become the collecting duct. So the collecting duct here and the loop of Henle, the pin, the hair pin, they lie in the same neighborhood, the neighborhood of the interstitium. It's this interstitium that needs to be flooded with solute. It's this where you need the HOMI. Okay, that's one thing. Then the second thing to know about this diagram, how it's made, is that when you see these arrows, okay, this arrow here, and this swinging arrow, this arrow here, and then this arrow here, remember that this means that you have fresh fluid coming from PCT into your loop of Henle. Just stay with this program here. So this is what this means. When you have this scenario where you see that the thick ascending limb of loop of Henle, and at the level you have these strong arrows, these dark arrows. Remember that this is part of the single effect. I'll explain it to you in a bit. Just remember what I'm saying. This is the single effect, followed by the dashed arrow in the in the subsequent slide. So you see now a pattern in these slides. You have a picture, a stage rather, a phase where you see these arrows where fresh fluid is coming in. Then you see a combination of two pictures here, right here. So you brought in fresh fluid. Then a single effect happened, which is depicted in these two pictures. Okay. Then the single effect happened. Then again, you have a repetition. You have fresh fluid coming in. Then again, the single effect is happening. Okay. And then this step is repeated many times, such that the osmolarities really start to look very angry. Now, if you compare this with, say, this, certainly this is a serious number, 1200 milliosmol. It's a very high osmolarity. In fact, this is the upper limit of HOMI. HOMI can be concentrated up to 1200 milliosmoles, and consequently, concentration of urine can be raised. Osmolarity of urine can be raised up to 1200 as well, not above that. So here you pick up the concept of HOMI dictating the osmolarity of the urine. The maximum that you can create, concentrate the urine, is 1200 milliosmol, and that the reason for that is that that is the maximum capability of HOMI in the interstitium. More of this will make sense to you as we go along. Now let's go into the nitty-gritty of it. Now that if you have understood what I've set up, so say this is when everything was at peace and honky-dory, nothing was happening, no excitement. But as soon as this now goes into this is where the dehydration has happened. Plasma osmolarity has gone up. Now you need to, ADH has gone up. Now you need to create HOMI. And so the single effect will come into play. If you remember, I've been mentioning single effect earlier as well. This is that very, very interesting ability of the tubule to separate solute from water. And again, I will repeat that sodium is an osmol, which basically means that it does not like to travel alone. It will always want to take water with it. That's the case. And if you want to only reabsorb solute and not let water follow, that is called the single effect. That usually cannot happen in any other part or any other tissue except the renal tubule. Okay, and except in the renal tubule, only in the thick ascending limb of loop of Henle, which is also called the diluting segment, is where this effect mainly can be seen. So check this out now. The 300, there was 300 everywhere, right? 300 was in the fresh fluid that was coming in from the PCT. Again, the thin descending limb, the thin ascending limb, and the thick ascending limb. Anatomically, this is not correct. Of course, these are supposed to be thin, and then this area is supposed to be thick, but stay with it. It's a simple diagram. I think it's from Guyton, so it will help you. That's why I selected it. So everything is 300. Now, when you turn the charm on, when you turn the single effect on, what happens? What happens is this is 300. When it came here, so it encountered that symporter, the sodium potassium 2 chloride symporter, right? Yes. What did it do? It pulled the solute from in the lumen and pumped it into the interstitium. Yes, but did not allow water to follow because the water is permeable. These is this epithelium here is impermeable to water transport. The water stays back. What is the result of this one simple effect? That you raised a tad the osmolarity of the interstitium, and in comparison you diluted the osmolarity of the tubular fluid, because remember, you removed the solute but did not let water follow. So you did two insults to the tubular fluid here in the thick ascending limb of loop of Henle. You snatched the solute away from it, but kept the water there and did not allow the water to follow. So naturally, what is left behind is diluter as compared to what came in. Okay, what came in was 300, but what ended up here is basically because of this action is now diluter. So uh, this interstitium will get a bit rich than what it was before, because it has now received a paycheck of solute. Okay, and hence it has become 400, while the osmolarity of this fluid has become 200. Okay, if you have understood this, that's great. That's the initial phase of the single effect. Now, you have created a slight increase in osmolarity in the interstitium. Yes. And since it's a hairpin structure, it's a hairpin structure. Hairpin structures are important in thermoregulation and in this scenario, what you're reading now, the concentration of urine. In the sense that if this were a straight tube, you would have very different situation. Simply, you could never have concentrated urine. More of this later when we'll talk about the maintenance of HOMI. But it's very obvious to see that if you do something to the fluid here, which has a bearing on the interstitium here, this interstitium is the neighborhood. This is where the descending thin limb also lives. So the fluid, which now is moving inside the thin descending limb, is exposed to the same interstitium, the same neighborhood that you created by doing this action. So what happens? What happens is this fluid, which was in the thin descending limb, it's water permeable. We've spoken about it. It will give out its water. Why will it give out it? Simple osmosis. It will give out its water because the interstitium outside is more osmolar as compared to this. It was not the case here, but because of this first phase of single effect, you added solute here. This added solute will cause an osmotic drag on the water inside the thin descending limb, and the water will come out. These dashed lines is movement of water. The strong lines are movement of solute. So now you understand. This water will come out of the interstitium, raising the osmolarity out inside the fluid that is left behind in the tubule. This is very obvious. That extra water will be picked up by the vasa recta and taken away. So this 400 will be preserved, right? This is the single effect. These are the two phases of the single effect. What is the first phase? Again, I'm revising now, is the pickup of solute from the tubule and dumping it into the interstitium by the thick ascending limb of loop of Henle. This creation of the extra osmolarity in the interstitium then has an effect on the thin descending limb of loop of Henle, where water is pulled out, raising the osmolarity of this fluid now, and the extra water is taken away so that this is not disturbed. Okay, now you have done one cycle. This is one cycle. These three diagrams are one cycle. The first, then the single effect, and then that's that. Now you just need to keep on repeating this cycle. But the difference is that you have changed things. You have changed the osmolarity of the incoming tubular fluid. You have changed the osmolarity of the interstitium, and the solute single effect will will take place anyway, but now it will take place on this changed fluid that you have created. So now this 400 will be pushed forward because new fluid of 300 from pre-city has been pumped in. This has been pumped in. This will push the 400 osmolarity carrying fluid forwards. It will now come to the thick ascending side of things, and it will be acted upon by the single effect. Now you can see that that 400 here, okay, will again, you will have the single effect. The symporter will pull the solute and dump it into the this interstitium, and now you see that that 400 became 300, while the 400 in the interstitium became 500. Okay. Uh, Before I go move on to this and finish this subject, you will see a mathematical symmetry in these diagrams. Whenever the single effect would take place, remember this. Remember the factor of 200. This is a cheat to understand or and remember these figures. You don't have to cram them. Whenever the single effect will take place, there will always be a difference of 200 between this fluid and this fluid, always. So you see 400 and 200 is, the difference is 200. Okay. Now when you brought in 400 here, oops, when you brought in 400 here, again the single effect happened, made this 500, the rest was 300. What is the difference? 200. Yes. And as it goes up above, this is the maximum osmolarity at any given time. But as I mentioned, as you go towards the cortex, the osmolarity drops. So as you go up, this 500 actually is 350. But again, the difference is always 200. So this is an important thing to remember. Okay, now just to complete the cycle once again, so that the concept is solidified, uh, this 500 here will then attract water out of the descending thin limb. Okay, water will come out as is shown here, leaving behind even more increased osmolarity. From 400, it has now become to 500. That extra volume is now, the extra water is taken away from the vasa by the vasorector, so that this is preserved. You keep on repeating the single effect. You keep on bringing fresh fluid, which I'll say it in the reverse direction now. You bringing the fresh fluid of 300 into the thin descending limb of Leucophene. It will come across increasing gradient of osmolarity in the interstitium as it moves along the thin descending limb, giving away its water, becoming concentrated itself, and by the time it hits the thin ascending and especially the thick ascending limb of Leucophene, it will naturally give up its solute from the tubule to the interstitium, raising the interstitial fluid osmolarity even more. And this cycle sort of goes on and on and on till it becomes this. Okay, this. So at the tip of the loop, you can have a situation where the osmolarity has risen to 1200, which will obviously induce a 1200 osmolarity change in the fluid that is coming in the system and going up and out. Okay. Now, some concluding remarks about this. You see, you have understood this single effect, I hope, and eventually, let's talk about what's happening here. So, in this area, you have hyperosmolarity in the interstitium and inside the tubule. But as you move up, because you are taking out a lot of solute from here, you are diluting the segment, you are making water abundant inside the tubule and taking solute out, using the solute to attract more water out of the thin descending limb. This is the story up till now. Yes? Uh, and you have understood the trick here. The trick here is to use the solute to bring out water out of the thin descending limb. Okay, so this is one source of that extra water that I was talking about. But the main situation, the main thing will come when you put consider that this DCT will then become the collecting duct. Okay, and it's this collecting duct here, which I'll show you in a bit, is where the ADH has already made inroads for that extra water to come in once it's available. Remember, ADH has inserted those aquaporins. Okay, so the stage is set. This interstitium, this here, is also available here. It's in the entire neighborhood. The whole neighborhood has become hyperosmolar. So collecting duct, this fluid of uh, this diluted fluid, heavy in water, which you have created very cleverly, now when it comes in the collecting duct, it has absolutely no choice but to give away most of its water to the hyperosmolar osmolarity through the newly made aquaporin uh, motorways under the able leadership of ADH, and that water, that precious water, is now given away, taken away by the vasorecta, which improves the, eventually addresses the osmolarity of the hyperosmolar plasma. Okay, this is the countercurrent multiplier, and this is the overall slide. You see that it's working. This is the single effect mediated hyperosmolarity. The picture now is complete. You have this collecting duct here. Okay, and this is the membrane which is ADH sensitive. Okay, this is where the ADH expresses those aquaporins, and you see that the fluid that came towards this area was dilute. This is where, look at this 100, and in fact this becomes about 300ish as soon as it's starting to hit, come back into the hyperosmolar environment, because it is now made to give out its water, a bit of salt as well, and we'll talk about the urea in a bit. So when you remove water from the fluid in the tubular fluid, what remains behind is concentrated urine, because you have taken away this water. The whole point was to reabsorb extra water. So once again, from cortex to medulla, you have created a hyperosmolar environment, so that you don't let uh, that extra water that in the tubular fluid that would have gone out, and in any case, you don't let that go out. That this hyperosmolarity drags that water in. You can see the role of ADH providing those aquaporins and all of that. So this is the HOMI and the increased ADH, which basically saves the day in a plasma hyperosmolar situation. Okay, these are the main points. Uh, Now the urea cycle, very briefly. Uh, it may look like a cluttered slide, but it's simple really. Urea is a waste product. It's cleared from the plasma. It, as you can see here, strong arrow. It's put out in the PCT, and it just flows around throughout the tubule. What is peculiar now is the following. You see that this line here, this epithelium here, has been shown very strong in dark color. This is where urea cannot go out. It's trapped inside the renal tubule. This is something which raises the concentration of urea, because uh, all sorts of things are happening in the fluid inside, but urea cannot do anything. Urea has to stay in, and hence it gets concentrated. Okay. uh, by the time this fluid hits the ADH sensitive areas, remember ADH, and now you will recall that when you read that info slide of ADH in the last lecture that we discussed, you saw that ADH not only reabsorbs water, it also enhances urea uptake. Okay, so ADH actually in this area where it's most active, not only inserts aquaporins, but it also stimulates the insertion of UT1 receptors, urea transporter, UT1, urea transporter 1 receptors here, so that urea can leak out into the interstitium. Why would we want urea to leak out in this particular scenario in the interstitium? Because we are creating HOMI. Okay, we have spoken about the HOMI of sodium. Now we are talking about that other 50%, the urea. So check this out. The urea will exit from the collecting duct, the inner medullary collecting duct, into the interstitium, adding to the hyperosmolarity. Okay, but then it does something which sodium doesn't do. It's that it's secreted, and this is important. It is secreted into into the loop of Henle. So uh, here you literally trap urea. Whatever urea is coming from this tubular fluid, you take it out inside, keep it inside the interstitium, and then when it goes up to a significant concentration, you start to secrete it inside the lumen. Back it goes, does the whole journey back again, and so on and so forth. So you excrete less urea in concentration of urine scenario, the dehydration scenario, than you would have done normally when water was available. Because now you're using urea ingeniously to add to your HOMI, and you're trapping it in a circular fashion. Okay, I hope you understood this. You are secreting it, then it goes up and comes down. You reabsorb it from here, and then again use it to attract water and all that stuff, secrete it back, and keep on using it till you've had your fill, you have reabsorbed enough water, and the plasma osmolarity has gone up again. So this is that urea cycle that I was talking about, the 50% of the HOMI. Footnote here is that urea is a metabolic waste product. Guess which metabolism does it come out of? Protein, right? It's a protein metabolic waste product. So people, interesting fact, people who are vegans or pure vegetarians, uh, would they have the same amount of urea that a non-veg would? Of course not, because they don't eat animal protein. All the protein that they get is from vegetable sources. Okay, so the urea in these people is less. Urea production is less. Hence, the urea cycle, availability of urea for the urea cycle is less. So yes, now you know where I'm going. The ability of these people to concentrate their urine in dehydration is less, because HOMI is dependent on sodium and urea in concentration in dehydration scenario. So pure vegans will have trouble concentrating their urine because of this fact. So this is a interesting fact to note. Now, before we go to the last part, uh, let me recap what we have discussed till now. We discussed dilution of urine, where water is abundant. No rocket science there. You just remove the solute at the thick ascending limb of Flucofenle, and you let water go out. And there is no idiot, so nothing spectacular is going to happen. Now you understand that that part of the situation was simpler, right? You appreciate that now. The story becomes interesting when you want to when you go into dehydration, right? When you go into dehydration, you need to concentrate urine. It's that it's there that you need some extra situation, extra mechanisms, and that extra mechanism is countercurrent mechanism, by creating HOMI, which then provides the extra pump, extra attraction for extra water to be reabsorbed. This HOMI is created collectively by sodium and urea. We've discussed countercurrent mechanism and the single effect and all that. This is the Urea cycle. Now, the HOMI that is created in the interstitium uh, is the same place as I mentioned earlier, where reabsorbed water is also coming through. So you may have a situation, you will have a situation where this water will dilute this interstitium. Okay, and the whole story goes down the drain. So no, that does not happen. is because along this tubule, you have the renal tubular network, which also goes side by side along these long limbs of long loops of loop of Henle. Okay, it runs along them and forms a countercurrent exchange mechanism, which conserves the HOMI for as long as you want. Okay, this is the thing. This is now what we are discussing. The first thing was HOMI creation. Now we are talking about maintenance of the HOMI. Remember that uh, creation of the HOMI, the mechanism is called countercurrent multiplication. You multiply solute inside the interstitium, and by that you attract water. Okay, there's a reason I'll tell you why I'm emphasizing this. This is countercurrent exchanger. Countercurrent exchanger is the vasa recta, and that is to do with maintenance of the HOMI. Now, why the emphasis? Is sometimes a very unfortunate thing happens when you are asked about countercurrent exchanger in an SCQ and in your exams, and you, in your hurry, write down countercurrent multiplication. You can imagine uh, what kind of marks would you get. The examiner asked you the exchanger, and you, in your hurry, did not understand that, and you wrote down the completely a completely different mechanism. So again, there is no cramming here. If you remember, countercurrent multiplication means all that single effect, uh, 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 pump, trapping all that solute, multiplying it with each cycle. That is the countercurrent multiplier. However, the vasa recta is the countercurrent exchanger, and we will see why are we using the word exchanger. Okay, so word of caution: be careful, read the question carefully. Okay. Now, there are two mechanisms by which vasa recta saves the day. There are two mechanisms how vasa recta basically maintains, helps the HOMI do its job. One is, it is just like the loop of Henle, it is a looped structure. It's not a straight line. It's not a straight tube. It is in loop. Okay. The only difference is the flow of blood is opposite than flow of tubular fluid. Okay. Now, one is the hair loop structure of the vasa recta. So, what is coming down is being affected by what is going up, and both of the coming down and the going up, both bloods are being affected by the neighborhood, the interstitium, just like the loop of Henle. Just like the loop of Henle. What you did at the thick ascending limb of loop of Henle had a bearing on the thin descending limb of loop of Henle. Yes? So the descending limb, the blood in the descending limb of the vasa recta will be influenced by what is happening in the interstitium. And when it trans does a transaction with that interstitium, whatever change happens has an effect on the ascending limb of loop of Henle. I'll tell you what's going on. Okay. Second point is the sluggish flow. If I don't know if you remember, we mentioned this right at the beginning of the renal lectures when we were discussing the functional anatomy of the renal tubule, the whole thing, the nephron. And I mentioned that as you go deeper into the medulla, the overall flow of blood decreases, right? If you remember that, it's the least in the inner medulla. That now has come to the fore. This is the sluggish blood flow through the vasa recta is important. You don't want a high velocity blood to go through this whole system, because remember that high velocity fluids have a washing away, quote unquote, washing away effect. If you increase velocity of this fluid, it will tend to wash away the fluid because the solute will not have time to be reabsorbed back in the ascending limb. We will talk about this. So just remember that the fluid, the blood flow through this vasa recta, the deepest portions of the medullary interstitium is slow. This also helps in keeping the HOMI intact. Okay. Now, let's see the hair loop structure. If it were not a hair loop, what would have happened? Well, disaster. What would have happened? Okay, you would have put in a fluid. Okay, imagine that this is the neighborhood. This is the same. You have the interstitium with increasing osmolarity that we have discussed just now, being created by the HOMI, right? And instead of the loop, the hair loop, you have a straight blood vessel going through and through, right? Okay. This is an interesting, good exercise. Not explained in Guyton as such. Okay, the comparison is not there. Guyton only discusses the hair loop. I discussed this lack of hair loop as well, just to show you how important the hair loop structure is. Okay, now, in the straight tube, when you introduce a fluid with 300 milliosmol osmolarity, it won't have significant problems right in the beginning because it's 300 outside, it's 300, everybody's happy. Okay, but as it goes down, as it goes deeper, it then comes across increasing osmolarity, the HOMI. The more deeper it goes, the more uh, concentrated environment it goes into. What starts to happen? The blue arrows depict the water. It starts to give out its water and it starts to pick solute, right? So it just goes down, literally goes down the drain, giving out its water, picking up solute. By the end of this straight tube, what started with a value of 300 has now become 750. Okay, and what started with 300 and should have been 600, 900, and 1200 is now basically 1000. So one circulation of blood through this straight tube raised the osmolarity of blood from 300 to 750, obviously because it gave out its water and picked up a lot of solute. And where did it pick the solute from? From the precious HOMI scenario, atmosphere. Decreasing the HOMI concentration of solute or its osmolarity, the whole point was to maintain it, and hence the match is lost. Okay. Now let's see the beauty of all you need to do is just uh, 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 put a loop in this long tube. Make a loop, not a straight line. Just make a loop like this, like this. So this tube is here. It's the descending limb. It loops and then becomes the same tube becomes the ascending limb and exits. Okay, this has very important implications. So the same discussion is when the blood is coming back into the system, it's 300, say for example, just to explain it to you. 300, when it comes down, it encounters an increasing HOMI, 600, 900, and maybe 1200 if we are working at the top speed, a top concentration. The countercurrent multiplier is really churning away. So as this 300 goes down the descending limb, it will pick up solute, give out its water, right? That it did here as well. Okay. So by the time it hits the tip of the loop of the pin here, hair pin, it becomes one with the interstitium. The osmolarity is 1200, the osmolarity is 1200. Okay, it reflects the same. However, it's not a straight tube. It will now pin back on its own. And remember, this distance is shown, this is not the case. They are, the descending and ascending limbs are, they lie very close to each other. Okay. So what now happens is you are parading this blood that you brought in, and all sorts of things happen to it. You're parading this blood back out of the ascending limb, uh, from the same neighborhood but in a reverse direction. And this reverse direction makes all the difference. How? Now, this hyperosmolar blood, when it goes through the ascending limb, it now goes through that hyperosmolar interstitium in the reverse direction. So as it rises through the ascending limb, it comes across a decreasing gradient of osmolarity. Yes, it's clear. So what will it do? It will pick up water, it will give out its solute. There you have it. As it ascends, It keeps on doing it, picking up that water, giving out that solute till it exits. So what happens in the net? The net is you take out water out and very less solute. This is the net. There are important implications, important summaries coming up, but I'll pause here so that you understand what has just happened. The hairpin structure, basically what it did is it conserved the solute of the interstitium and took away the water, its own water, and also the water that came out of the leukophenoid and the collecting duct. Capiche? You happy with that? I hope you've understood it. Again, these are not replacements for your own reading. That reading is very important. Those discussions over cups of teas or coffee or whatever you have with your colleagues is very important. These things, physiology it nourishes, flourishes, develops based on discussions. Okay. So, having said the bare bone thing, now I'll come to the important conclusions. The obvious thing we've done that the water that would have messed the HOMI is picked up by the vasorector and taken away. That's one thing. There's a salt implication as well, an implication, a complication related to salt. Remember NaCl, it crystallizes, right? Uh, it would, if you allow it to stay in one place, it will tend to form crystals. Yes. So in countercurrent multiplication, you are dealing with a lot of sodium chloride, and you're dumping it in an area where there is interstitium. Interstitium is not known for its traffic, is it? What is known for its traffic? The tubule, lots of fluid is passing through it. The vasa recta, it's a blood vessel, a lot of blood is passing through it. But what happens in the interstitium? Interstitium is just a space, right? And you're dumping so much solute in there, you always run a risk of making crystals there. So vasa recta, another function of vasa recta is keeping it real, keeping it fluid, literally. The salt should remain a salt in granular form, not make crystals, because that will create a lot of issues, as you can imagine. So the moving vasa recta keeps stirring the interstitium, pushing in water, stirring it a bit, picking it up, and so on and so forth. So it keeps on stirring it like you stir your tea with a spoon. Yes, so that crystal formation is inhibited. Another thing is, if you notice the 300 and the 350, if you noticed. So this osmolarity of the leaving fluid is a tad more than what came in, right? So any extra salt is also taken up by the vasorector. Any extra salt, okay? So you need just enough salt to create the HOMI, do the benefit, the business of extra water reabsorption, but at the same time not form crystals. Okay, so HOMI does both. It has got the stirring effect, and then it picks off your extra top up of salt so that you don't have any untoward issue in your interstitium. Okay, and the sluggish flow we discussed, it needs to be sluggish so that that doesn't run off with a lot of solute. That's that. We've discussed the HOMI maintenance, vasorecta, uh, and this is where we consulted these references. Once again, my emphasis is to read up on this at least within the first 24 hours of this watching this video, so that you get a very nice picture of what we've discussed. Any questions that get generated by that reading will get generated when you read it within 24 hours or as early as possible, basically, because connections are made in learning, and questions are generated where they need to be generated. If you delay these matters and read it somewhere outside of this time frame, then it's like reading it for the first time. Okay, so let's avoid that. Take the benefit of watching this video, investing this time, and read it straight away. Okay. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.